All right, it's not picking up. Nope. Hello, everyone. Is the microphone working? Yes, I hear the microphone. Good morning, everyone. Could I please have your attention? We will start class. Okay, so today we're going to be finishing up CPU virtualization, and then we'll be talking about how the OS virtualizes memory. So we'll be spending a couple of lectures on how we provide address spaces and that abstraction to processes. So a couple of announcements. You all know that Project 1 was due last night, right? And so I think that went pretty smoothly. We didn't see a lot of last-minute problems, so I am thrilled you all turned something in. I assume if you are here today, I'm happy that you're all sticking with this. If you were able to get the first project done, you're going to be able to get all the rest of these projects done as well. It will just take more time and more effort, but they will certainly all be doable. So Project 2 is now available, as you all know. It's using this XV6 toy kernel framework that you need to run on an emulator. And so kind of getting comfortable with that code base, it will take you a little bit, but we are going to be using this XV6 code base for the whole semester. Later, you'll be adding more complex functionality to it, like maybe messing around with the page tables or how the scheduler works or how the file system works. So anytime that you do put into learning that code base now, it will be worth it. But for now, all you really need to know is how to get it running and how the system calls work and just a few of the basic data structures. So in discussion section tomorrow, the TAs will be doing a little bit of a walkthrough about the XV6 organization and how systems calls work in that environment. But your time in discussion section will be much more valuable if you first look at the project spec. So is it it's the microphone problem. I hate microphones. Okay, but I thought it was picking up. Is it when I turn my head, it comes in and out? Who knows? All right. See, that doesn't feel like it's picking up. And then sometimes it does. If I talk it down the whole day, it'll work great. Great. Okay. Oh, well. Well, you'll just have, oh, there you go. Okay. You can hear me. All right. So that's, I read the instruction manual. They're like, put it right there. OK, now that's working better. OK, now it will be smooth for the rest of the semester, we hope. OK, and so there are a couple of homeworks due as well that if you go in Canvas, there's these very easy quizzes that are meant to just help prepare you for the midterm exam. So the idea with those quizzes is we show you the right answers at the end, so you definitely should just keep taking them until you get all of the questions right. They're not going to be worth many points, but it will make sure that you understand how basic scheduling works. So any questions? So we do have 2 more short quizzes that are available now, and they'll be due 1 week from today. But again, they're very, very short. Recommend you do them, though. Yes? It does not affect your grade if you take it. Nope. Take it as many times as you want. It just saves your highest score, which should be the max number. Yes. All right. OK. So today we're going to be talking about virtualization. We'll finish up our topic on CPU virtualization. We'll talk about process creation, which we had not talked about before. And then we'll review the multi-level feedback queue scheduler, since I went over that a bit quickly for some. Then we're going to start talking about memory virtualization. So why do we need to virtualize memory? What is an address space? How is this going to work? What are the different approaches for virtualizing memory? So we're going to spend a couple of lectures really talking about all these different ways. We're going to start up with a very naive, bad approach, doing some static approaches, then make it dynamic, then add more hardware support, and so on. OK, but let's go back to CPU virtualization. So I kind of skipped over how you create a process, and so I wanted to go over this in a little bit more detail because this is going to be very useful for you for Project 3, which is going to be creating a shell. So there are 2 different ways that operating systems tend to create processes. The first, we'll call option 1. There you just build a new process from scratch, like an empty, null process, and then you get it started running some executable that you specify. The second approach is what Unix does. The idea here is that you fork a process or you make a copy of an existing process, and then you just overlay the new executable that you want to run. So let's look over the pros and cons of that a little bit. Okay, so option one, you create a new process from scratch, and then you tell it what executable you want it to run. So the way that basically would work is you specify this executable, and that lives in the file system, and so you'll load that code and the static data that's associated with that into memory. You create an empty call stack that you're starting off with no procedures. You create and initialize this process control block, or PCB, and you put that in the ready list, because that's the structure that's basically in the ready list. And you'll want to make it look like when you're starting up this process that it has just finished a context switch. That you'll remember when we looked through those steps of what happens on a context switch and how we were saving registers to the kernel stack, and then we were saving the registers again into the PCB. When a process is scheduled, it always looks like it just finished running that line of code where it was doing a context switch. So that's kind of the default stage. You want it to make it look like a new process has also just gone into that code of where it was doing a context switch. That's kind of like our invariant there. So some people really like this model. You're doing really the minimal amount of work. It seems very intuitive that this is how you would start up a new process. The problem is it's going to be really hard to properly initialize that process with exactly the environment that we want it to have. So think about all the permissions that you might want to give this process, what you want all of its environment variables to look like, how you want it to write to standard out or read from standard in. There's just lots of things to configure about a process. So when operating systems take this approach, like Windows NT, they'll tend to have like a huge argument list for like all the different variations for how you might want to start up this process, where you really have to specify exactly where it should read from standard in, what different limits should be, and stuff like that. Okay, so that's approach one. We're not really going to be using that in this class. So the option that Unix does is basically you take an existing process, and then you make a copy of it, or you make a fork of it, and then you change it in the ways that you need to. So we're going to see in a lot of detail that Unix has this fork system call, and it basically just makes a perfect copy of the calling process. And then immediately after that, you call exec, and it will overlay your current process, the one that's calling exec, with the file image that you've specified here. Okay? So how does that work? So fork makes a copy of the current process. So you have, by default, all of the permissions and the limits and the environment variables set up exactly the same as the current process. And you just make a copy of that and save it. You have to make a couple of changes to make it so that you can tell that it's a child process instead of the parent process. So what are the things that you might want to change here? So one's pretty obvious. You're going to want to make it have a new process ID. It has to have a new identifier that has to be different from the parent. And then a more subtle thing is we are going to change the return code that's been pushed onto the stack so that when the child returns from fork, because remember, it has the exact same stack as the parent, so when it calls return, it's going to return back from that fork system call as well. The only difference is going to be that we've pushed a 0 to the stack of the child so that it can look at the return code and see that it's the child, whereas the parent will have the return code that's the PID of the child. So each of them can tell who they are in this relationship and then do work accordingly. Okay, and so then what will often happen is that the child process will call exec, and that is like you put your executable here, and it just replaces all of your current code and your current data, static data, with whatever was specified there. So this is a pretty straightforward way to do things as well. The problem is that it can be pretty expensive. If you really did do a complete copy of the parent process's address space, it could be a lot of work to do all that setup when you're just going to call exec and waste all of that. So there are some implementation details we'll get to later when we understand memory a bit more about how you can avoid some of that work. But it could involve a bit of extra work then that you're just going to throw away when you call exec. Okay, so let us look at some kind of pseudocode, kind of C code here. So this is emulating what a Unix shell does. So think about the shell that you use all of the time. It's just sitting around in a forever loop, and it's printing out a prompt to you and getting a command from you that you would like to run. It then calls fork, and then it looks to see from that return value from fork, because two processes are going to return after this statement, after this call to fork. We'll have two processes running. Not just threads, two completely different processes. The child process will see that the return value is 0,
And so this child, it will eventually call exec on the command. And then if the exec returns, that means there was an error, because it should go off and run ls or your mydiff process or whatever it was. And it shouldn't return here at all. If it does, it means exec failed, because we've overlaid our code segment. If this is successful, we don't know about this code anymore. And then meanwhile, what does the parent do? The other process sees that it's the parent. It remembers what the return value was, and then it calls wait on that PID. So what that does is it doesn't go through the loop until the child process exits. That's what this wait system call does. And so that's useful, because if you didn't have this wait here, the parent process would just run to the top of this loop again, and it would look to get another command, and you would just be able to do all of these things. So this forces it to wait for the process to continue. So this is what you would usually do if you're putting a process in the foreground, right? If you put a process in the background with like an ampersand, you don't wait for that process to finish before you ask for the next one. So that's the basic difference between foreground and background processes. Does the parent shall wait or not? Okay, so what I wanted you all to focus on is that there's this beautiful amount of space between when the child process starts and when it calls exec. And what's beautiful about that space is that you can write any code that you want there to modify the environment of this running child. So you can set up how you want that command to be executed, right? So you could set different limits for that child process, or you could sandbox it, you could redirect its I/O. So I'm going to talk a little bit about file descriptors, since that's going to be useful for project 2 as well. In XV6, you're having to deal with file descriptors and what their value should be. So we'll talk about this a lot more in the last part of the course, where we're going to talk about the file system and how to obtain persistence. But here, this is just kind of a very high-level API issue that I thought would be useful for you to look at. Okay, so what are file descriptors? File descriptors are just simple integers that index into a table. And the table then has a lot more interesting information that we'll learn about later, like it's tracking the offset of where you've read in this file, and lots of metadata information and how to actually read that file. But what's important for us is that this file descriptor table tracks all of the open files, and it's just a simple index that we can use to access a given file after it's been open. So for example, if you call open and it's a new file, we're going to start where this is going to return file descriptor 3 in this example, because by default, standard in, standard out, and standard error are file descriptors 0, 1, and 2. You have those open by default with every program that you run. Okay, so why is this interesting? So what's really awesome is this lets you do redirection really easily in a shell. So what is redirection? So like when you run a command and then you said, please redirect its output into a file instead of printing to standard out. So how can we do that? It's really, really awesome. Okay, so the idea is that the shell, in that time it has before it calls exec of ls, so going back, so the shell, it's seeing that ls is the command that it's going to run. Before it execs ls, it's going to call close and muck around with the environment that ls is going to see there. Okay, so the shell, when it sees this redirection, it says instead of putting the output of ls to standard out, we want to put the output to this other file instead. So the way that we can do that is the shell just calls close of standard out. And so then file descriptor 1 is free, it's empty. And then we open new file.txt, or any other file, whatever we said here. And the OS, the policy that it implements is it takes the first available file descriptor and uses that for this newly opened file. So now file descriptor 1, instead of pointing to standard out, it'll point to some data structures that let us write to new file.txt. So what that looks like is now in your program, if you do an fprintf to standard out, it doesn't show up on your terminal, it doesn't show up on standard output, it actually shows up in new file.txt. So certainly I encourage you to play around with standard out redirection in your shell. Just make sure you've used the little redirection symbol for something. And then in project 3, you're going to be implementing this as one of the features of the shell that you add. Okay, so I know there's going to be a ton of questions about this once you actually get to Project 3, but this is the setup for it so that you will know what that is saying when we talk about it. Yes? Each process has its own. Very, very good question. This is per process. There are some shared data structures across processes, but this one that we're talking about is absolutely per process. That's a great question. Yeah, this would not work if you were mucking around with other processes' open file tables. Yep. All right. Okay. So that was completely new stuff. Now let us go back to some of the scheduling that you saw. So we'll start off with some easy scheduling. Yes?
What happens if we do not close the file?
If we do not close the file?
We open the file. If we do not close it, if we do not close the file, does the file, empty table still have that file?
Okay, so you mean like if in our example here we didn't close standard out, if we just directly called open on new file?
We just open new file.txt. It takes one of the indexes.
Right, then it would have given us index 4 as the file descriptor for new file.txt.
What happens if I keep on opening files and do not close it? Does this table get occupied completely?
Yeah. You just keep allocating the next lowest available integer to that file. And so there is some limit on how many you can have. And it's some system configurable thing. It's a pretty large number, like 256 or 1,000 or something like that. But you'll see in XV6, it's going to be a very small number so that we can kind of stress that and see when they've all been allocated. More? Yeah?
This is a per process.
Per process.
So say that I have another process and I start opening files there as well.
Uh-huh.
Then would it say, it would also have 3 copies of 0, 1, and 2 pointing to the same file descriptors. And then for the other process, it will be an exact copy. Say I open 3 files here, created
Yep.
another process, and I open another file here. So say 3 for that process will be pointing to the first file that I opened for the other process.
It's completely separate. So I think we'll get into the details of that more later, but for now, just think of it as completely separate. There is no interaction at all between what's going on in one process and another process opening files. Yeah? Oh, no, as long as your process eventually calls exit, at that point everything will be closed for you when you call exit. Sometimes we're just being a little particular about you doing all of that stuff because eventually if you have to write a long-running service, something that needs to be going for days, it's kind of acting like a user-level OS. You need to be really careful with tracking resources and making sure that you close everything. But generally when you call exit, all of these resources that are associated with the process will be freed. Yeah. Uh-huh. That's how we were going to think about it for today. Yeah, that it's just taking this away. And now, because you have to figure out what should we do with this other stuff, how do you free that? But we don't care today. For today, once you close that, you're just taking away that entry. Yeah. Setting that to null. Yep. Okay. Awesome. Okay, so back to scheduling. So spend a minute, talk with your neighbor, figure out which one of these 4 pictures corresponds to which one of these 4 schedulers for this particular workload here. So it should just take you like a minute, get the answers. All right, so let's hear your answers. So what's the first picture? First picture must be round robin. It's using time slices and going between them all. I can't quite figure out what the time slice is here. It must be that it must be less than 5 if this one's ready to go when it's its turn, hopefully. So that's round robin. This one here must be shortest job first, SJF, that at time 0 it has a choice between A and B. It chooses B as a shorter job than A, so B gets to run. It is non-preemptive, so when C arrives at time 5, the scheduler doesn't get to do anything. But at time 20, when B finishes, it then gets to look at C and A, and it says, oh, C is shorter than A, and so it runs C next. All right, so that was shortest job first. The next scheduler is clearly shortest time to completion first. So at the beginning, it chooses B, but then when C arrives at time 5, it then compares the remaining runtime of B, which is 15. 10 is less than 15, so it preempts B and runs the shorter job C. Then when C is done, it looks at the jobs that are left. B is less than A, so it'll run B. And then time for first come, first serve, or first in, first out. It just runs the jobs in order. So any questions about those theoretical kind of building blocks for our schedulers? Great, so you should be able to calculate turnaround time, response time, and you should be able to draw these Gantt charts if you're given a workload and told to assume you have a given scheduler. That's what quiz 2 is about. Okay, quiz 3 is looking at that multi-level feedback queue scheduler. So you'll remember we're going to have some number of queues. Highest priority queues are at the top. We have some number of ready processes that are at each queue. If you have 2 processes that are at the same priority and they're both ready, you're going to round robin between them. These jobs will always run instead of the lower priority jobs. So like C will only run once A and B are blocked on I/O or exit the system or their priority degrades down below C. Great. So I showed this figure in class, and based on the questions I got after class, I don't think most people knew what all of these various colors meant. So please take a minute and talk with your neighbor and try to explain what I was trying to show in this figure, and then I will go over the figure to make sure you're all interpreting it correctly. All right, so let me explain the figure to you all. Yeah? What's your question? You have to ask the whole class at this point. You want to ask you a question? So this example, we're not adding any gaming to it. So in this example, we're assuming that B and C, and I'm glad you assumed B and C were the same 2 jobs that I did. B and C are not demoted because the scheduler doesn't have a gaming mechanism. So it's just saying as long as you relinquish the CPU before your time slice ends, it will keep it at the same level as before. So what's going on in this example is we had process A. It was the only process in the system. It started off at Q2, it used up its time slice, so then it got demoted, and then it used up that one and it got demoted again. So then at this point here, 2 new jobs, B and C, arrive. They're doing lots of I/O. They start off at a higher priority, so they are scheduled first. So B runs for a tiny bit of time, and then it does I/O, so it blocks. It's no longer in the ready state. And so C gets scheduled at that time as well. So this is a duration that's shorter than the time slice that we could see back here. And so the scheduler is not demoting any of them because it's always relinquishing the time slice, the quantum before the time slice expires. So we keep alternating between B and C as they do I/O. But then this starvation mechanism kicks in and notices that job A hasn't been run for some amount of time. So maybe it boosted it up to Q1, maybe it boosted it up all the way to Q2. We'd have to specify the details there. But some starvation thing kicks in, and we raise its priority, and so then eventually it gets the full time slice. Now, at the end of that time slice, it's going to get demoted down to this level here, but it's not going to get to run down there, right? Because B and C are using up all of the CPU, and it's a lower priority job. So it's sitting in the queue here, but it's not getting to run. So that's what I'm trying now to show with dashed lines. But then that starvation mechanism will, again, periodically run. It notices that process A is never running, so it increases its priority so that it is at the highest priority, and it gets to run again, gets downgraded, and that continues forever. So, yes?
When A gets promoted, after it's run at the top level,
Yes.
when it gets re-demoted, does it go down to the bottom level where it was at, or does it go through the queue?
It would go through the queue. It would follow whatever policy we had in place before. That our default policy is you use up the time slice, you get demoted by 1 level. And then here, if we used up the whole time slice, which we're not going to, then we would have been demoted as well. Does that answer that? Great. Yes?
ABC, when all of them are at the top priority, they should run in round robin. So why is only A running?
So what's happening is, B is using the CPU for a little bit of time, and then it's blocking, and so there's no job left to run. And then C runs and then blocks. So that's why those two are moving back and forth so quickly. Now, the time slice at Q2, it is this long. So that's why when job A gets the CPU finally, it does get to run for a longer period of time than the others, because it's not relinquishing the CPU. It's using up its whole time slice. But then once it gets demoted down here, then the jobs that are at the higher priority, B and C, are going to get to use the CPU again. Yeah?
Since A used all of its time slice, why didn't it get demoted again?
Here, it used all of its time slice, so it got demoted again. That's what I'm trying to draw with these dashed lines to show it gets demoted, it just doesn't get to run there. Yeah. Yes? That's my drawing ability. Yeah. This is me using PowerPoint. Yeah, not too precise. Yes. Okay. All right. Moving on. Right, so this is in your third quiz. It should be pretty straightforward to do. If you have any questions, let me know. Okay, so that is it for virtualizing the CPU. Now we're going to talk about how to virtualize memory. Okay, so the first part of this course is all about virtualization. How do we give the impression to different processes that they have exclusive access to the resources or to the hardware on this machine? So virtualizing the CPU was relatively easy, I dare to say. It just took us about 2 lectures to talk about mechanism and policy. Virtualizing memory is going to be a bit more complex. This is going to be about 5 lectures. We're going to start off with approaches that have a lot of disadvantages and then slowly remove those disadvantages until we get to what modern systems do. Okay, so today will be the light and airy one that has lots of problems. Okay, so a high level, why do we need to virtualize memory? So in the earliest systems, we did not virtualize memory. When you had a running program, it could be the only running program in the system, and it shared memory with the operating system. So there was no protection between the running program and the OS. If this program decided to accidentally overwrite the OS, you completely crash your system. You'd have to reboot from scratch. You could read anything you wanted to or write anything there, but it didn't really matter because you were the only process running anyways. There was no other processes that you could be stealing their information from. Okay, so it was easy to do, But it's really pretty ridiculous to have a machine where you can only run one process. If you look at how many processes are running on your desktop machine, it's going to be hundreds or thousands, right? Okay, and the process can destroy the OS. Okay, so we want to provide real true multi-programming, and there's a number of properties that we're going to want here. So first, we want to have it be transparent. We shouldn't have to do anything special in our process to make it share memory with other processes. It should work regardless of how many processes are running. We absolutely need to provide protection. It shouldn't be that one process can read or write the memory of the OS or any other process in the system. That would be bad if you could steal secrets from another process. We'll be concerned about efficiency. We want to make sure we're not wasting memory or RAM that we have in our system. We'll be talking about this metric fragmentation. That's like these little small spaces of memory that you can't use. And we won't want to slow down processes either, obviously. And then a kind of a subtle, more difficult property that we will eventually be able to provide is sharing. That if you have two cooperating processes, they might want to be able to share just portions of their address space or have some shared memory that they're each able to access, even though they're not able to access each other's complete address space. So we'll get to that towards the end. Okay, so you've learned about address spaces in 354. Let's kind of go over that. So basically, the address space of a process is the process's view of memory. And so all of its program code is going to be in its address space, its heap will be allocated in the address space, and the stack is allocated in the address space. But the illusion that the OS is going to provide is somehow we are going to map this virtual address space that each process sees to physical memory over here. So what's going on in physical memory in this ridiculously tiny machine here is that in physical memory, we actually have the OS running, we have different processes running, and somehow it has to be the case that process A can't read or write process B's data, right? So how are we going to do that? So let's dig into what's actually in an address space in a little bit more detail. This is probably review for you. So we'll have some segment that we'll call the code segment. There, my pointer's dying, which stinks for me. Okay. We'll have a heap. So the heap is where, when you call malloc, that you have dynamically allocated memory. That's where that's going to be allocated. And then you have your stack, where we will push procedure frames and have all of your local variables there. So one key thing is that we have some static portions. Our code, that's a statically sized segment. It doesn't grow over time. And all of our global variables that we knew about when we started. And then the heap and the stack, we don't know how large they're going to be, and so the safest way to let them both have as much space as possible within our address space is to put each of them at the two extremes and let them grow towards each other. So if you have a sufficiently large address space, you're not going to run out of addresses, and you'll be able to have as large of a heap and as large of a stack as you want. Okay, yes? Well, so certainly it just changes over time with needing to have more bits. You know, that like a 32-bit address space would have been standard a while ago, and now we have many machines that will give you a 64-bit address space. So it's basically you just want to give as many bits as possible so that we can have more memory allocated to processes. But I mean, we're going to get into more the sizing of everything, I think, as we get into the details of these structures. I think we'll get into that later with how do we move things around there. All right. Okay, so high-level stuff. Why do we need dynamic allocation of memory? We all know that you don't know ahead of time how much memory a given process is going to need. This process needs to have some data structures, a tree, whatever it's doing. You have no idea how much it's going to need, and so we need to allocate that memory dynamically. We need to have dynamic memory allocation because of recursive procedures. You don't know how many times a procedure is going to be called. You can't pre-allocate or statically allocate the stack for that. Anytime you call malloc, because you have some complex data structure, we don't know how many times you're going to call malloc, so this is going to be dynamic. And as you all know, there's two different types of dynamic allocation. that we see in programs. We have the stack, and we have heap allocation. So the idea of the stack, it's a general data structure, but it's also what we use for allocating procedure frames and local variables. The key feature of a stack is that you have to free memory in the reverse order that you allocated it in. So if you allocated A, B, and C, the first item that you'll have to free will be C, and then if you allocate D, then the next thing you'd have to free would be D. Okay, so I know this seems really obvious, but what's awesome about this data structure from the OS perspective is just how simple it is to manage. That we will just have a single pointer that's showing where the top of the stack is. And that single pointer separates what's been allocated from what is free. We don't have to have all this complex managing of what's free versus allocated. And we have no wasted space at all. There's no fragmentation. There's no holes in what's been allocated. So when we can use a stack for things, that's awesome. So let us review what goes on in the stack. So let us look at this. When we have main, and then we have int A is going to be allocated on the stack, right? It's a local variable. When we call foo, the return address of main will be pushed on the stack. The parameter that we're passing will be pushed on the stack. So then when foo is called, it's able to access the variable that's been pushed on the stack, which now has the name z. It has a local variable as well, so that gets allocated on the stack. We call printf, then we return from foo, and we're able to pop off the stack the parameters that we passed, as well as the local space we just allocated for A here. And then what we stored on the stack was the return address that we need to return to back in main. So we're able to figure out where we need to return to. So I think you've learned about how all that stack gets set up in past courses. And we're just going to assume that all of that is working here and build on top of that. OK. So that was the stack. Our heap. So we use the heap when a user process calls malloc or new or whatever it is that your language provides. The idea of malloc on the heap is that you can allocate and free in random arbitrary orders. And the way this is basically going to work is the OS just gives like some library, your malloc library, a big chunk of free space that there's this system call called sbreak that the OS extends your heap and gives that space to the user level library, and then the user level library manages that allocated space and doles out little pieces to the process that's calling it. And so that user level library has to have some data structures with tracking which memory is free versus allocated. And when you ask malloc for a certain amount of space, it searches through its data structures and finds the right size. So the problem with heap managed space is that it will have a lot of fragmentation, and we'll see this in other domains later. But basically, what will happen if you try to allocate 20 bytes? That would be problematic because there aren't 20 bytes that are contiguous. And if you need 20 bytes, you need them to be contiguous. There's lots of different ways to kind of solve that problem. You would have to defragment things, move the allocated space together, move all the free space in another area, and then you'd be able to do those larger allocations. But we are not really going to talk about the details of how you implement malloc because, again, you may have implemented something like malloc in 354. So we're going to assume you know how to organize the heap as well. OK, so the review here to talk with your neighbor is we have a bunch of addresses, and you should figure out where those things will be allocated. Is it static data, code, stack, or heap? I think you can do this in about 1 minute.
right. Okay, so I think the first three are straightforward. Int x, that's a global variable. It's static. We knew that that existed when we compiled the program. Main is code. That's compiled. Y, that's a local variable. It's allocated on the stack. Z, what is Z? Z is also a local variable allocated on the stack. But that local variable that's been allocated, it's a container. It's a pointer to something else. But Z itself is absolutely allocated on the stack for main. It's a local variable of main. So then here's the interesting one. The thing that Z is pointing to, that container, what is it pointing to? It's pointing to memory that has been allocated on the heap. So the contents of Z are going to be the address of something that malloc has returned, an address that lives in the heap. So if you look at what Z contains, it will be an address that lives in the heap. Okay. Any questions? All right, pointer fun. Okay, so let's look at some more memory addresses. So this is a very lovely C program, pretty straightforward. Let's look at what it looks like in assembly. So you can disassemble compiled code using a variety of tools. And what you might see is assembly code that looks like this. And what you will see is kind of nice. So these are the addresses of the instructions where main lives in the address space. What is move of this into this? So this is a user register. And then we are looking at the base pointer on the stack because X has been located on our local stack. And we're looking at something 8 away from the base pointer. And that's where X has been allocated. So we move the contents of X into a register. Then we add 3 to the value that's in the register, and then we move the new value in the register back off into the stack here, right? Okay, so that's some assembly code. So that's the setup for our OS question. So what I want you to all figure out, we're really going to become obsessed with memory accesses. Can you figure out how many memory accesses it's going to be to execute those 3 assembly instructions? And extra credit, what are the memory addresses going to be? So this will take you more than 1 minute. Please talk with people around you. Yeah? Do you have a question?
Is AMD 64 since we're using R registers?
What?
This is not IA32.
This is just like, it's some mishmash of assembly.
I just noticed when I looked at assembly code on the Linux machines, it was
So my assembly is always going to be like sort of right, sort of, don't ever like trust the details of every little thing up there. But yeah. All right, so let us look at what addresses we are going to access when we execute this program. So the first address that we are going to read from will be what? The first address we will read from is where the instruction pointer or the PC is pointing to, which is this address right here. So that is our first access. We fetch the instruction that's at that address. Yeah, can't forget those instructions. Don't focus only on data. Then the next memory access that we make will be relative to the base pointer. So we know our base pointer is hex 200. We add 8 to that. And so we'll do a load from this hex address here. That will be someplace on the stack. So we do a load from there into this register.
Then our next instruction that we will fetch is at address 13. We then do an exec of that instruction. Are there any memory accesses associated with that instruction? No, it's just modifying a register. Then we fetch the next instruction at 19. We exec that instruction, which is just doing a store of what was in this register back out into that memory address that's on the stack that's at 200 plus 8 at 208 there. All right, so 5 memory accesses to run this tiny little easy program. And we're going to be looking at a lot of detail on how do we translate these virtual addresses to physical addresses and what that means. Okay, but these are all virtual addresses, things in the process's address space. This is what you have been familiar with up until this point. Okay, so that was all background, what's going on in virtual address spaces with heaps and stacks and virtual addresses. Now we're going to start getting into, well, how do we actually virtualize memory when we only have physical memory to dole out to all of these different processes? So the problem is, as we've seen, when you compile your code into an executable, there's all of these addresses in there. So we're going to have to figure out how the address in one address space, when it's the same address as another process that it wants to access, that's actually going to different places. So depending upon our time, we'll talk about 4 mechanisms for doing virtualization: time sharing, static relocation, base, and base plus bounds. Okay, so the worst thing that we could do that would allow us to virtualize memory would be to time share memory. So this would be ridiculous, but the idea would be we have our code and data statically allocated on persistent store. We create this process for the first time, and we allocate its heap and stack and get this process running. So process 1 is the only thing resident in memory, except for the OS, which is also there doing something, but we're ignoring that problem here. When this process is done, or when we need to do a time slice and do a context switch out, then the OS will copy everything about its current state, everything in memory, back out to disk. The OS chooses another process to run, creates it, runs that for a while, decides that it wants to switch to another process, writes that out, and so forth. So this is going to be ridiculously slow. It doesn't make any sense in the modern era to be doing all of this copying of this huge amount of memory. But this is what earliest systems would have done, since it protects processes from one another, and you can't tell that other processes are running. So let us keep that quick, because that just has ridiculously poor performance. And we don't want to do time sharing. It's clearly going to be better to do space sharing, that we have a lot of physical memory, and it will be better to dole up that memory and give different amounts of it to different address spaces. So all of our remaining solutions will always use space sharing. Okay, so another early idea that we no longer do is what's called static relocation. So the idea here is that we are going to figure out ahead of time, before we start this process, exactly where that process is going to run in physical memory. And so then we will actually rewrite its executable, its binary, so that all of its addresses go to where it's been placed in physical memory running this time. So this is doable. It can have very good performance. It's just, you can imagine, it's a horrendous thing to have to rewrite an executable. So the idea here is we had our, does this work? Are you, oh, that's awesome. Okay. So we have our standard code here, and then we take all of the memory addresses and we change them to where they're going to be located in physical memory. So for one process, the addresses for the instructions are here. For another one, the instructions are here. And we just rewrite it. So if we had any accesses to static data, that would have had to have changed. We don't have to rewrite the accesses that are relative to the stack, because that's just all stack relative, right? It's still just 8 from our base pointer, and we'll just have different contents in our base pointer for where the stack lives for each of them. Okay, so the intuition here is that both processes are living in memory together, and we'll rewrite where the addresses live, and we don't have to rewrite the operations that are relative to the stack, since those are all relative anyways to a different value. All right, but this does not work very well for a number of reasons. So first of all, there's no protection across different processes. If this process is able to generate an address that is down in this process's address space, it could just read and write from those addresses. There's no hardware protection. There's no OS protection preventing that from happening. So that's one problem, no privacy, no isolation. Another problem is that you can't move these address spaces after they've been placed. You did all of that rewriting of the binary to adjust the addresses, and then later if you want to move somebody around, you couldn't do that. Okay, so static is also poor. Okay, so let me give you all a break. Maybe talk with someone you don't usually talk to. What was their experience like with Project 1? What's their work style like? You're trying to get to know as many people as possible in this class. You're going to be looking for future project partners. So it's nice to find who has similar styles to you. All right. Okay. We're going to start talking about our other styles of virtualizing memory. So the previous approaches all had really fatal flaws because we didn't have any support from the architecture. So we definitely need some hardware support here so that we can provide better isolation. So the most basic version we'll look at, it starts to have a memory management unit or an MMU. You want to think of the MMU as some piece of hardware. Maybe it's on the same chip as the processor, but it's some piece of hardware that's taking the instructions that the CPU is generating, and it's translating those from the logical addresses that you see in your user-level process, and it's translating them to physical addresses that you cannot see unless you connect some hardware probes here, what the physical addresses are that are actually accessing memory. Okay. So again, MMU, it's hardware. It translates the logical addresses that you are aware of at your user-level process to physical addresses that actually access RAM there. And so sometimes instead of logical address, I might use the term virtual address. And sometimes instead of physical, we might say real or machine. Those are all basically synonyms there. Okay, so in our simplest version of dynamic relocation with some hardware support, what do we need? The MMU needs to be aware of what mode we're running in. So are we in that kernel or that privileged or that protected mode? Then we can do certain things, whereas if we're just in user-level mode, we can't. So when you're in the OS and you're in privileged mode, then it has to be the case that you can execute certain privileged instructions that you couldn't otherwise. And we didn't have a lot of examples of these privileged instructions before, but one of those would be modifying the contents of the MMU, telling the MMU what it should use in some of its registers. And so also when you're in this privileged mode, the MMU will know that, and we might be then able to access physical memory directly rather than having our logical addresses translated to physical addresses. Okay, but then when we're in user mode, when that bit is set to show that we're in user mode, then the MMU is going to translate all of our logical addresses that we're generating to physical addresses. Okay, so what does that look like? So this is the simplest example of an MMU. It's going to get much more interesting as we go. But our starting version, it has that mode that I was talking about. It's tracking, is it in kernel or user mode? And then it has a base register. And so this would be the number of bits that you have in your architecture. We're just assuming a 32-bit architecture, but it could be 64-bit architecture. So the idea is a logical address comes in. If the mode is equal to the user, then we are going to add the base register to that logical address to generate a physical address. If it's the OS that's running, then we'll just send that address that it's generating directly to physical memory. Okay. So this is going to be great. It's going to give us a lot of power because now we can dynamically change addresses. So we just use this base register. And so every process that runs, it will have a different base register, and that's showing where its address space lives in physical memory. And so now when we do a context switch, part of that context switch will involve changing that base register in the MMU, right? So let's look at some pictures. So now we have two processes. They are running the exact same code. They're accessing the same addresses in their logical address space, but those addresses have to be different in physical memory. So for example, in virtual memory, process 1 is doing a load from memory address 100, and it's clearly 100 in its logical address space. And then when P2 does a load of 100, it is clearly, 100 in its virtual address space there. Okay, so the key then is that we're going to have this base register that points to the base or the start of our address space. And so when we do a load from 100, we just add 100 to the base register, and that's the physical address that we need to generate. Okay. So that will be enough to do a lot of things. So here's a straightforward quiz for you. So who is it, or what is it, that's actually performing the translation of addresses using that base register? Process, OS, or hardware that's doing that? That's hardware. That's what the MMU is doing. It's using the base register to just add on to the logical address to show where that address space lives in physical memory. And then which is the entity that's actually determining the contents of the base register and modifying that and telling the hardware what it should hold. That's the OS that's doing that. That's OS is privileged, so it can modify and access that base register. The OS is determining where a process lives in physical memory. It's doing that allocation, and then it's telling the hardware, this is where I've placed that process in physical memory. Okay. All right, so are we done? Of course not. We are very far from done. So one question, with this base register, can we protect two processes from accessing each other's address spaces? So can P2 hurt P1? Can it read or write P1's address space? Well, look at how I've numbered these things here. It's all unsigned numbers, right? These are not, you have no negative numbers. So P2 cannot hurt P1 because it can't generate a physical address that's smaller than 4 kilobytes here. So any address that it sends, do I have a good picture of this? Remember that picture, whatever address it generates in the physical, in the logical world, it gets added to the base register. So it's always some value that's at least 4K or higher. Does that make sense to everybody? Whereas P1, if it generates a large address, it's going to get added to this base, and it could then access this physical memory down here with our simple hardware that we have so far. Right? So for example, if P1 does a store to this decimal number, which I will not usually use, but I have decimal in here, if we do a store to logical address 3072, it adds the base of 1K to that, and so we end up doing a store at this physical address here, which is in P2's space. So just having a base is not a good solution. We are not protecting one process from another. Right? Okay. So there's another simple solution to this one. We just add a bounds register. So we just make sure that the addresses that a process generate are not larger than its address space, right? So we'll still have our base address. It's the starting location of where you're placed in physical memory. It's the smallest physical address that you'll generate. And then we're going to have a bounds that's just saying this is the size of your address space. And if your process generates an address that goes beyond the bounds, it will cause a segmentation fault. Your process will be killed. You've done an illegal memory access. So the implementation of this in the MMU is still very, very simple. We have our base register, we have our mode, but now we're adding a bounds register. And so now we always check to make sure that the logical address that we want to access is less than that bounds, that it's in our address space. And if it is not, then we send an error back to the OS, It's a trap back to the OS, and the OS can kill the process that did this thing. I mean, the OS could do whatever it wanted at that point. It has whatever policy makes sense, but the policy that makes sense is to kill the process that did that and to tell it that there's a segmentation fault. Okay, so simple example, process 1 is running. We've set the base register in the MMU to be P1's base register, and the bounds register will be P1's bounds register. And then when we do a context switch and P2 is now running, we will change those registers in the MMU to match P2. And so now I do not think it is possible for either process to access each other's memory. So now when P1 tries to do a store to this address that goes beyond its address space, what's going to happen? The hardware will tell the OS that there was an error. The OS gets this interrupt. The OS then figures out how it wants to handle that interrupt. It sees that it was process 1 that was doing something that caused that to happen, and so it delivers a seg fault to that process and kills that process as a result. So by just having a little bounds register to compare to, we can make sure that processes aren't generating illegal addresses. Okay? All right, so now just think about what you need to do on a context switch. Every time we switch between processes, we need to change the base and bounds register in the MMU, so that's something that we're going to have to track. That's going to be part of that process control block, something that's in that PCB that's tracking everything that we need to know about this process, all of the registers and stuff like that. So now when we do a context switch, we change to privileged mode. We save the base and bounds of the old process that was running into its PCB. We load the base and bounds registers in the MMU for the new process that was saved in its PCB, and then we change back to user mode and jump to the new process. Okay, so question for you, what would we be implementing if we didn't change the base and bounds register when we did a switch? So we changed still all the registers, let's say. We changed the stack pointer. We changed the PC, but we don't change the base and bounds register when we do this context switch. No, these are, we're actually trying to do something useful here. There's something interesting that we can do if we don't change the base and bounds. Yeah? That's an interesting guess. I think you're on the right track here, but that's like basically what threads are. That threads are a context switch to a new execution stream with its own registers, its own stack, but it's sharing the same address space as the other thread that was running there. So it shares some of the same state as the other thread that was running, but it's going to have its own registers. So we'll be looking at threads in a lot more detail when we start looking at concurrency. All right. But of course, user processes can't change the base and bounds registers, and user processes can't change to privileged mode without doing this context. Okay. All right, so base and bounds gives us a bunch of advantages. We can support dynamic relocation. We can move processes around in physical memory, right? If you decide to move the address space of a process from one physical memory location to another, all you have to do then is you copy everything, and then you change the base register to show where you've copied it to. So we can move things around if we have some fragmentation and new processes arrive. This is really cheap to implement. It's very little logic. It can go very, very fast. Okay. But it's going to have a bunch of disadvantages. So it's still the case that our address space has to be allocated contiguously. So you need to know ahead of time what's the max address space a process can have. And this is going to be ridiculous. So you don't know ahead of time how big this process's heap needs to be or how big its stack is going to be. So you have to give it, a large address space. And with this design, with just a base and bounds, all of that has to be contiguous. So you're going to be allocating 2 to the 32 bytes for this thing. It just doesn't make any sense in a modern architecture. Because basically, you have to still reserve all of this empty space here, because when you're generating addresses and you want to get to the stack, those are the addresses that are at the end of this logical address space. So you'd have to allocate all of that. And then another problem that we're going to see in more detail is that you can't have any partial sharing across processes. So two processes can have the exact same address space, which is what we would have with threads, but it's not going to be possible for two processes to just share code or to have some shared library or to have some memory segment that has some variables in it that they want to be able to communicate with one another. They have to share everything or nothing with the approach that we've done. So we're going to need some new approaches that allow us to share just portions of our address space. So to fix all of these problems, we are going to go through a large list of improvements, but not today. So in our future lectures, we'll start looking at how to have segmentation. Then we'll add paging to that. Then we'll have segmentation and paging. Then we're going to have multi-level page tables. And then we're going to add TLBs to that. So that will be fun, and you'll learn a lot. All right. So you can look at some announcements while you go. And if you have any questions, feel free to come and talk.